Hello everyone, hope everyone's having a good time at Fringe. My name is Stephen Donegan and I'm here to present our InSAR analysis for two dam failures. The Saipan-Sainamoy Dam in Laos and the Brumadinho Dam in Brazil are recent dam failures we studied. The goal of the study was to improve the understanding of the collapse and hopefully help prevent these tragedies in the future. Each set of imagery was processed using equivalent processing chains with only small changes to accommodate data differences and resolutions. I'll briefly touch on step 6. Error estimates are derived from a three-component model using atmospheric variability, changing surface conditions, and errors in elevation model. We use the uncertainty estimates to calculate the signal to noise, or SNRs, which provide an estimate of the significance of signal measured in the context of the noise floor of the data. At the end, we have a set of measurements we can investigate a number of different ways. In each dataset, we derive displacement time series, average displacement rates, and signal to noise ratios. The data was examined for spatial patterns and temporally looking for accelerations in time series. We place an emphasis on both presenting displacement and the associated SNR in order to characterize the significance of any signal. While we knew the fate of these dams, we aimed to avoid fishing to confirm any signal as a precursor in a known failure area. An overview of the data used for Brumadinho. We acquired data from as many sources as possible in order to give us the best picture of the site and allow for cross-validation. As a first step, we looked at the short-term analysis. The next slides will look at pre-failure interferograms for each of the four datasets. Some isolated points of possible high displacement on the dam can be seen in each, but no large-scale features. You can also see in the back of the tailings a consistent purple-yellow signal corresponding to settlement of the tailings. The second sentinel, the TSX. And finally, the CSK. A large signal is visible across the dam. Due to its size and shape, it is likely an atmospheric signal. While some signal can be interpreted as possibly something happening, when we try and identify anomalous trends, we need to keep in mind the history of the site. The challenge is identifying which one is anomalous, which interferogram is the one just prior to failure. At this scale, they're not strikingly different. Next is to look at the rates for progressively longer-term measurements in order to increase the SNR and sensitivity of detection. No significant displacement was observed in the 3 and 6 month rates, so we focus on the 1-year measurements in the next few slides. These all use 1 year of data. We see agreement between the 4 datasets in the back of the tailings. The 2 sentinel datasets showing a bit of interesting features lower on the dam wall. If you are expecting to find a signal, one could pick one out from this area. These areas are interesting, but we need to ask what's the noise level and what's the chance of these spots occurring due to noise alone. How can we have confidence the signal is real? We approach this through signal to noise ratios. This is a hypothetical example what it would look like. The distribution curve is an estimate of the likely noise that we model. On the left, an SNR of 2 represents a 95% confidence that the signal is not due to noise alone. As datasets can be millions of points, it's important to keep this in mind in terms of false positives. On the right, an SNR of 6 is extremely unlikely to be due to noise. Another hypothetical example of a point with higher noise, more in line with what we see at Brumadinho. We're looking at the same 1 year as before, now displaying SNR estimates colored from 0 to 5. We've contoured the SNR level 3 in white, and we see the tailings material at the back consolidating where the displacement signal was apparent. There are some areas on the dam corresponding to the higher rate in the sentinel data that are reaching an SNR of 2, seen with the thinner white line. This technique gives us an area to investigate next, so we'll look at the time series of points in this area, labeled A. The average time series of the selected points is shown in red. All 4 datasets display approximately 2 centimeters per year of displacement, and which is consistent with long-term settlement of the dam. Shorter time span in the TSX and CSK, and high spread of the individual points suggest higher levels of noise, possibly the shorter wavelength interacting with vegetation on the dam. Seasonal trends are seen in the sentinel data corresponding with local rainy seasons. We directly looked for accelerations using a tool that calculates the acceleration between portions of the time series and quantifies the significance of these accelerations. None were found on the dam face. A number of kinks at different points in the time series are highlighted. The signal 1 at the end of the top time series does not appear to be anomalous when considered against the rest of the time series. Other kinks are also highlighted, occurring at times when the dam did not collapse. We performed the same analysis over the Saipan Sainamoy site, where the results were very different. The dam is outlined in red. Displaying the 20 previous slides in one slide, now we're showing the monitoring output program, where the rate, signal to noise, and acceleration detection are all concisely displayed. By selecting a point within the SNR contour on the dam, the time series and error estimates are displayed. We set out to study the dam failures as if we didn't know the dams had collapsed. In Brumadinho, there was no obvious statistically significant precursor signal. In Laos, the areas where the signal to noise were greater than 4 and the statistically significant accelerations were both detected on the dam. It is important to consider the noise present in datasets and its impact on monitoring programs. Thank you very much for taking the time, and thank you to the organizers. Have a great day.